All right. So, for this deep dive, you really sent over some, I gotta say, pretty mind-blowing stuff.
Yeah,
This is like the deep end of cosmology, right?
absolutely.
And I think the thing that really just hits you right between the eyes is this statistic
Oh, yeah.
that everything, and I mean everything, we can see and understand. So, stars, galaxies, planets, us,
Right.
and all of that only makes up about 4% of the entire universe.
It's a pretty wild thought, isn't it?
It's wild. It's like
Yeah.
96% is stuff we label as dark, which basically means we have no clue what it is.
Yeah, Tark is just a placeholder for we don't know.
Yeah, exactly. And of that 96%, we've got like 23% that we call dark matter,
Right.
and then a whopping 73% that's dark energy.
Yeah, it's the lion's share of reality, as far as we can tell.
It's unbelievable. And one of the sources you sent over has this quote from a theorist, and I mean, it's almost funny.
Oh, yeah. I know the one you're talking about.
He says, we're just a bit of pollution. Get rid of us and everything else we've ever thought of as the universe.
Right.
And very little would change. We're completely irrelevant.
He says it with such cheer, too.
Yeah, it's almost cheerful.
Yeah.
But it really makes you think, where do we fit in all of this? It's not just like, oh, there are some missing pieces, right? This really messes with our understanding of gravity, like the very fabric of reality.
It really does. What's fascinating to me is the whole story of how we even got to this picture in the first place.
Yeah.
It's an amazing intellectual journey. And the sources you picked out really trace that adventure.
Yeah.
How scientists, step by step, over decades, came to this, honestly, pretty strange view.
Right.
And it wasn't like a sudden eureka moment.
Yeah.
It was this gradual buildup of discoveries.
Right.
Each one kind of peeling back another layer and leading to even more questions. And like you said, this isn't just some abstract theoretical physics thing.
Right.
This is about how we see ourselves connected to the cosmos and realizing the limits of what we know.
Exactly. And to kind of set the stage, one of the key sources, and I think the one we'll be leaning on most today, is The 4% Universe by Richard Panik.
That's a great book, yeah.
It's really well written, and it lays out this whole historical narrative, all the scientific insights that led to this, perplexing view of the universe. So to really understand this, I don't know, what you call it, this darkness that surrounds us.
Yeah, the cosmic darkness.
Yeah, we need to rewind the clock a bit.
Yeah.
Let's go back to, like, the dawn of modern cosmology.
Okay. Yeah.
So this is before dark matter, before dark energy. Any of that even shows up on the radar.
Right, back when cosmology was almost considered, well, not quite real physics.
Oh, really?
Yeah, the book describes how, back in the early to mid-20th century, a lot of physicists saw it as bordering on metaphysics.
Yeah.
Almost like a holdover from pre-scientific times, where you were just trying to save the appearances, as they used to say.
Save the appearances? What does that even mean?
It basically meant finding models, mathematical models that kind of fit what you observed, but they weren't necessarily connected to any deeper reality.
Oh, I see.
But then 1965 happens.
Okay.
And is a real turning point. That's when we have the discovery of the cosmic microwave background radiation, or CMB for short.
Oh, yeah, the CMB. So that's basically the afterglow of the Big Bang, right?
Exactly. It's like a snapshot of the universe when it was incredibly young, just a few 100,000 years old.
Incredible.
Yeah, and the story behind its discovery is pretty amazing.
Oh, yeah, that's the one about Penzias and Wilson, right? At Bell Labs.
Right. They're working with this huge, super sensitive horn antenna.
Yeah.
Trying to get it ready for satellite communications. But there's this annoying background noise that they just can't get rid of.
Like they thought it was a problem with the equipment.
They try everything, even evicting a pair of pigeons that had made a nest in the antenna.
No way, pigeons.
Yeah, they were worried the pigeon droppings were messing with the signal.
That's hilarious.
It is right. But even after they get rid of the pigeons, this mysterious noise is still there. And they eventually realize.
They're hearing the Big Bang.
Yeah, they're picking up the faint whispers of the universe's birth.
Whoa, what a discovery.
It is, but here's the thing, and this is where it gets even more interesting. At the same time, at Princeton, you've got Robert Dick's team, which includes a young Jim Peebles.
Okay.
And they're actually building their own antennas specifically to search for this CMB radiation. They knew the Big Bang Theory predicted it.
Oh, wow.
So Dick gets this phone call, explaining what Penzias and Wilson have found, and his reaction is classic.
What, he was like, we're so close.
I mean, pretty much. He says something like, well, boys, we've been scooped.
So close. But that's got to be frustrating.
Yeah, I'm sure it was. But it's a great illustration of how science often works. Sometimes, discoveries happen by accident, and sometimes it's through dedicated, focused research.
Yeah. You mentioned Jim Peebles. He went on to win the Nobel Prize,
It
right?
did, yeah, in 2019 for his contributions to cosmology.
But it's funny because you said earlier that cosmology wasn't considered real physics, and here he is, this future Nobel laureate.
I know, right?
Eh.
It's kind of ironic. Peebles has even said that he originally thought cosmology was, not quite rigorous enough. He
Mm.
wanted to do real hardcore physics.
Yeah.
And his mentor, Robert Dicke, had a big influence on him in that regard. Dicke was all about testable theories.
Yeah.
If you couldn't connect your theory to an experiment you could do, in the foreseeable future, he wasn't interested.
So practical.
Yeah, very practical. There's this great anecdote in the book where Peebles is going on about trying to unify general relativity and quantum mechanics,
Yeah.
which is a huge problem, even today.
Right.
And Dicke just cuts him off and says, go find your Nobel Prize first.
So, like, worry about the small stuff before you tackle the impossible.
Exactly. But that's Dicke, always focused on the doable.
So you have Penzias and Wilson accidentally stumbling on the CMB,
Right.
and then you've got Dicke and Peebles trying to find it intentionally.
Yeah.
But even before all of that, you had Edwin Hubble's work in the 1920s. That was a big deal.
Huge. Hubble really revolutionized our understanding of the universe.
Yeah.
Before him, people thought the Milky Way was the whole universe.
Oh, wow.
But Hubble showed that there were all these other galaxies out there,
Yeah.
which he called island universes.
Island universes. I love that.
Yeah, it's a great term. And then, in 1929, he makes this even bigger discovery.
Okay.
He finds that these galaxies are moving away from us.
Mm-hmm.
And the farther away they are, the faster they're moving.
So that's the expanding universe.
Exactly. And he figured this out by looking at the redshift of the light coming from these galaxies.
Right. Redshift.
It's the Doppler effect, but with light.
Mm.
You know how a siren sounds higher pitched when it's coming toward
Oh, yeah.
and lower pitched when it's moving away. Same thing happens with the light. If something's moving away from us, the light waves get stretched out, shifted towards the red end of the spectrum.
So it's like a cosmic speedometer.
Yeah, exactly. And Hubble found that the faster a galaxy was moving away from us, the more its light was redshifted.
So not only are there all these other galaxies out there, they're also all rushing away from us.
And from each other, yeah. It was a pretty mind-boring discovery.
Kind of blows up the whole static universe idea, right?
Totally. And that's what sets the stage for the Big Bang Theory.
Right.
The idea that the universe began as a hot, dense state and has been expanding ever since.
Okay, so now we've got this expanding universe, the afterglow of the Big Bang. It's pretty simple, right?
Well, that's what they thought at the time.
But then,
But then things start to get messy.
the missing mass problem.
Exactly. Even as early as 1950, you have Vera Rubin.
Yeah, Vera Rubin. What an amazing scientist.
She was, absolutely.
Yeah.
So in her master's thesis, and she's already seeing these weird patterns in the way galaxies are moving.
Really? So early on.
Yeah, and it's kind of brushed aside at the time.
Oh, wow.
It's interesting, though. People like George Gamow and Gerard de Vauclair, they actually saw some potential in her work.
Huh.
But it takes a while for the mainstream to catch up.
And this is all while she is, raising kids, facing all sorts of societal pressures.
Absolutely. Back then, it was even harder for women in science.
Yeah.
But she was persistent.
Mhm.
She keeps studying the distribution of galaxies, how they're clumped together. And in 1954, she finishes her PhD with a thesis that really shows these clumps, these clusters of galaxies are a real thing.
Because of gravity.
Right, they're being pulled together by gravity.
Yeah.
And then in the late 60s, early 70s,
Yeah.
she starts working with Kent Ford.
Okay.
And they do this groundbreaking research on the rotation of galaxies.
So how fast stars are orbiting the center of a galaxy?
Exactly. And they start with Andromeda, our nearest big spiral galaxy.
Yeah.
And they're expecting to see, stars farther out from the center moving slower,
Makes sense.
like in our solar system, right? Pluto takes way longer to orbit the sun than Mercury.
Right, because it's farther away.
Exactly. But that's not what they see.
Oh.
The stars at the edge of Andromeda are moving just as fast as the ones closer in.
Oh.
The rotation curve is flat.
Wow.
Yeah, it's really weird. It's like Pluto zipping around the sun at the same speed as Mercury.
So, like, the laws of gravity are broken.
It seems like it. It means there must be way more mass in Andromeda than what we can see to create that much gravity.
Hmm.
But Rubin and Ford aren't the first to come across this missing mass problem. Back in 1933, Fitzwicky,
Okay.
he was studying the Coma cluster, which is this huge group of galaxies.
Yeah.
And he notices something similar. The galaxies are moving so fast that there's just not enough visible matter to hold the cluster together.
Oh, wow.
Yeah, he even comes up with the term dunkle Materie, which is German for dark matter.
So the idea's been around for a while, but it's like Rubin's work really nails it down.
Yeah, she brings a level of detail and rigor that really makes people pay attention.
And then Peebles and Ostrikers come along.
Right.
And they do these computer simulations.
Yeah.
And those simulations show that galaxies shouldn't even be stable
Right.
unless there's a bunch of invisible matter holding them together.
Exactly. They basically say, look, if galaxies only had the matter we can see, they'd fly apart.
So that's more evidence for dark matter.
Right. More evidence for this invisible stuff that's making up the bulk of the mass in galaxies.
It's crazy to think that everything we see, all the stars and gas,
Yeah.
that's just a tiny fraction of what's really out there.
It's a huge paradigm shift, isn't it?
What was Vera Rubin's reaction to all of this?
The book describes her as being, very focused on the data.
Yeah.
She wasn't really into the theoretical debates so much. She's more like, look, this is what the observations tell us. There's this famous quote of hers. Nobody ever told us that all matter radiated. We just assumed that it did.
It makes sense when you think about it that way.
Yeah, it's like we were only seeing the tip of the iceberg and we didn't even know it.
Okay, so we've gone from this relatively simple expanding universe
Yeah.
to needing this mysterious dark matter to explain how galaxies hold together.
Right.
But it doesn't end there.
Nope. The story gets even weirder.
Dark energy.
Dark energy.
The universe's expansion is accelerating.
Yep. So after Hubble discovers the expansion,
Yeah.
the big question becomes, how fast is it slowing down?
Right, because all that matter should be pulling on itself, putting on the brakes.
Exactly. And to figure this out, they need to measure distances to galaxies really precisely.
Okay.
And they use what they call standard candles, objects with a known brightness.
Oh, I've heard of that. Like
Yeah.
Cepheid variable stars, right?
Yeah, those are good for relatively nearby galaxies.
Yeah.
But to really see far out,
Yeah.
you need something brighter.
Supernovae.
Supernovae. And that's where the Berkeley Supernova Search Team comes in.
Okay.
So you've got guys like Saul Perlmutter and Carl Pennypacker.
Yeah.
And they're pioneers in using computers to automatically search for supernovae.
Really? Like this is the 80s, right?
Yeah, they're way ahead of their time. And there's actually a funny side story here.
Okay.
Perlmutter was also involved in this project called Nemesis.
Nemesis?
Yeah, it was this idea that the sun had a companion star
Huh.
that was like a Death Star.
A Death Star.
Yeah, the idea was that this companion star would periodically swing through the solar system and cause mass extinctions on Earth.
Wow, that's intense.
It is, right?
Yeah.
But that's another story for another day.
Right, right. So, back to supernovae.
Back to supernovae.
So the Berkeley team is trying to find these distant supernovae to measure the universe's expansion.
Right.
But it sounds like it wasn't easy.
Oh, it was really tough. They had trouble getting funding.
Yeah.
And at first, they weren't finding as many supernovae as they expected.
Oh,
But they kept at it.
good for them.
And then, in the mid-90s, another group forms, the Heisey Supernova Search Team.
Okay.
They're led by Brian Schmidt.
Yeah.
And they include guys like Nicholas Suntzeff and Adam Rees.
So now it's a race
It's a race.
to find these distant supernovae and figure out if the universe is slowing down.
Exactly.
And the type of supernova they're looking for is type Ia, right?
Right, type Ia. These are incredibly bright.
Yeah.
They happen when a white dwarf star explodes.
Okay.
And the thing is, they're supposed to be really consistent in their brightness.
So perfect standard candles.
Almost perfect. Yeah, so Mark Phillips and Nicholas Suntzeff, they realized that type Ia supernovae aren't all exactly the same brightness. But they figure out a way to standardize them
Okay.
by looking at how their brightness changes over time.
Yeah.
They can basically calibrate them and make them even more reliable as distance indicators.
Nice.
Pretty clever solution.
Yeah. And I think around the same time you have the Calantalolo collaboration.
Right.
And they're focused on measuring the Hubble constant.
Right. The Hubble constant. That tells you how fast the universe is expanding right now.
Okay.
And they're using type Ia supernovae to do it.
But there's a problem, right?
Yeah. They get this value for the Hubble constant that implies the universe is younger than its oldest stars.
Oops. That doesn't sound good.
Yeah, it's a bit of a paradox.
So lots of new data, lots of puzzles.
Exactly. It's a really exciting time for cosmology.
Yeah. And then you've got all these new ideas floating around, like cosmic inflation.
Oh, yeah. Inflation. That was a big one.
This idea that the universe went through this huge growth spurt in the first fraction of a second after the Big Bang.
Yeah, like a super fast expansion.
What was the point of that?
Well, it solves some problems with the standard Big Bang model.
Okay.
Like, why is the universe so smooth and uniform on large scales?
Yeah, that's weird.
It's called the horizon problem. And another problem is, why does the universe seem to be spatially flat?
Flat. What does that mean?
Well, it's a bit hard to explain without getting too technical.
Yeah.
But basically, it means the geometry of space is flat, not curved.
Oh, okay.
And inflation explains this by saying that the universe expanded so much, so quickly,
Yeah.
that it's smoothed out any initial curvature.
I see.
It's like blowing up a balloon really fast.
Yeah.
The wrinkles disappear.
Makes sense.
And inflation also predicts that the universe should have a certain density, a critical density.
Okay.
And this is where the cosmological constant, or lambda, comes back into the picture.
Oh, yeah. Einstein's biggest blunder, as he called it.
Right. He added it to his equations to try and make the universe static, but then Hubble showed it was expanding.
Oops.
But in the 90s, with all this talk about a flat universe,
Yeah.
lambda starts to look interesting again.
Okay.
Because if the universe is flat, but we don't see enough matter,
Yeah.
maybe lambda's making up the difference. So the race is on between the two supernova teams.
The Berkeley team and the High Z team.
Right. They're both trying to find distant supernovae
Yeah.
and use them to figure out how fast the universe is decelerating.
Okay.
And they're pushing the limits of technology. They're finding galaxies at record redshifts really far back in time.
Wow.
And then, in early 1998,
Mm.
both teams announced their results.
It's,
And the universe is not decelerating.
it's not.
It's accelerating.
Whoa.
Yeah, it's a huge shock.
So the expansion is speeding up.
Speeding up. It's like something is pushing on the universe, making it expand faster and faster.
Wow. And that's dark energy.
That's dark energy.
So we needed dark matter to explain why galaxies hold together.
Right.
And now we need dark energy to explain why the universe is accelerating.
Exactly.
What was the reaction to this discovery?
Well, at first, people were skeptical.
Yeah.
It was such a radical idea. Even Jim Peebles, he initially thought it was wrong. Yeah, he thought the data was pointing away from a cosmological constant.
Hmm.
And Michael Turner, he's another big name in cosmology.
Yeah.
He also had his doubts.
So how did people get convinced?
More data, more observations.
Okay.
The Hubble Space Telescope played a big role.
Oh, yeah. Hubble.
It was able to see these distant supernovae much more clearly.
Yeah.
And it confirmed that they were indeed fainter than they should be if the universe was decelerating.
So the acceleration was real.
The acceleration was real, and there was a lot of drama behind the scenes, too.
Oh, yeah. The book talks about the competition between the two teams.
Yeah, it was fierce, but also productive.
Right.
Like you had Alex Filippenko.
Okay.
He was originally on the Berkeley team, but then he joins the High Z team.
Wow.
So he's got this unique perspective on both sides of the story.
That's cool.
And then you've got Robert Kirshner.
Yeah.
He kind of weighs in on everything.
It's like a scientific soap opera.
Kind of, yeah. But it's a reminder that science is done by people, with all their personalities and ambitions.
Right. So we've got dark matter,
Yeah.
and now we've got dark energy.
It's like we had to call the tooth fairy twice. See,
The tooth fairy.
yeah, it's an analogy. Like, first we need this invisible stuff to explain galaxy rotation.
Dark matter.
Right. And then we need another invisible thing to explain the accelerating expansion.
Dark energy.
So it makes you wonder, are we just making stuff up?
Yeah, is this like epicycles?
That's the worry, right? Are we just adding more and more complexity to save the appearances without really understanding what's going on?
Right, right. So the big question is, what are these things? What are dark matter and dark energy?
That's the billion-dollar question, isn't it? We know they're out there,
Yeah.
but we have no clue what they actually are.
So what are the ideas?
Well, for dark matter, one of the leading candidates is WIMP.
WIMPs.
Yeah, it stands for Weakly Interacting Massive Particles. The idea is that these are particles that don't interact with ordinary matter very much,
Yeah.
except through gravity.
So they're really hard to detect.
Extremely hard.
But people are trying.
Oh, yeah, there are experiments like the Cryogenic Dark Matter Search
Yep.
or CDMS. They're basically trying to catch these super rare interactions between WIMPs and ordinary matter.
Wow.
It's a tough job. Like
Yeah.
the book says, it can be pretty disheartening at times.
Yeah, I can imagine.
And then you've got another candidate for dark matter,
Axions.
axions.
Yeah, these are much lighter particles than WIMPs.
Okay.
And the book makes this great comparison about the search for axions being a Red Sox
I'm a
fan.
Red Sox fan.
Yeah, years of hope and disappointment.
Yeah, I get it.
But there are experiments looking for axions, too.
Like what?
Well, there's the Axion Dark Matter Experiment, or ADMX.
Okay.
They use these huge magnets
Yeah.
to try and make axions convert into photons, which we can detect.
So, like, tricking them into revealing themselves? Exactly. And the theory behind it is pretty wild. They call it macroscopic quantum mechanics.
Wow.
It's kind of mind-blowing how quantum effects can show up on such large scales.
Yeah. And weren't there some other ideas for dark matter, too? Like machos?
Oh, yeah, MACHOs. That stands for Massive Compact Halo Objects.
Okay.
The idea was that dark matter was made up of things like, brown dwarfs, neutron stars, black holes,
Yeah.
things that don't emit much light.
Right.
But we haven't found enough of those to account for all the dark matter.
So WIMP is axions are the main contenders?
For now, yeah.
Yeah.
But even without knowing what dark matter is, we have this model that works really well.
What model?
The cold dark matter model.
Oh, cold dark matter.
Yeah, the idea is that dark matter particles were moving slowly in the early universe.
Okay.
And this model does a great job of explaining how galaxies and clusters formed.
Oh, really?
Yeah, it's been confirmed by these huge galaxy surveys, like the Sloan Digital Sky Survey.
So we don't know what it is, but we know how it behaves.
Pretty much, yeah.
And what about dark energy? Any good ideas there?
Oh, man.
Yeah.
That's the really big mystery.
Yeah.
There are tons of ideas, but no clear winner.
Like what? Give me some examples.
Okay, so you've got quintessence.
Quintessence?
Yeah, that's this idea that dark energy isn't constant.
Okay.
It can change over time.
Mm.
And then there's phantom dark energy.
Phantom dark energy.
Spooky. I know, right? That one's even weirder.
Yeah.
It could lead to this thing called the Big Rip.
The Big Rip.
Yeah, where the universe expands so fast that it tears everything apart.
Oh,
And then there's brain cosmology.
brain cosmology.
That one involves extra dimensions,
Okay.
like beyond the three spatial dimensions we're familiar with.
Mind-blowing.
It is, right? The book goes through a whole bunch of these ideas,
Yeah.
and it's kind of overwhelming.
So we're basically clueless.
Well, not totally clueless. We know dark energy is causing the acceleration.
Right.
We just don't know what's driving it.
Right. And part of the problem is that our two best theories of physics.
General relativity and quantum mechanics.
Yeah, they don't play well together.
Not at all.
Yeah.
General relativity describes gravity,
Yeah.
and quantum mechanics describes everything else.
Okay.
But when you try to combine them,
Yeah.
things get really messy.
So we need a new theory.
We need a theory of quantum gravity.
A theory of quantum gravity.
And that's one of the biggest challenges in physics today.
I think I read somewhere that even Einstein struggled with this.
Oh, he did. He was really bothered by this idea of action at a distance in gravity.
Action at a distance.
Yeah, like how does the sun's gravity affect the Earth
Yeah.
when they're so far apart?
Right.
He wanted a more local mechanical explanation.
But he never found it.
Nope. And it's still an open question today.
And haven't there been some alternative theories, too? Like theories that try to explain things without dark matter or dark energy?
Oh, yeah, there's MOND, modified Newtonian dynamics.
OND, right.
That one tweaks the laws of gravity
Yeah.
to try and explain galaxy rotation without dark matter,
Okay.
but it doesn't really work on larger scales.
Mm.
And besides, even our most cherished theories, like general relativity,
Yeah.
they need to be constantly tested.
Right. Science is all about testing.
Exactly, and that's what experiments like Apollo are doing.
Apollo.